Yes, then announce it. You are the chair for the session.
Yes.
Yes.
You have some announcement.
You have to announce, introduce. That's it.
Oh.
Yes.
Good evening.
So 1 second.
Oh, you too.
Say one more, and then I'll end it over to you. Okay, because I did not think about it. Yeah. Right?
Shall I start?
Yes, please start. Yes. Okay, so welcome back, everybody. And we are going to have our second public talk of this Indo-French astronomy meeting, which we are organizing with the Franco-Indian colleagues. Until now, it has been great. And today we are going to hear about medieval astronomy and how astronomy has evolved. But I will hand over to the chair of the session. I'm just happy to say that I had met Professor Shylaja 20 years ago when I was a master student. And I'm so happy today to be here and to see her giving this public talk. So please, Professor Ashwani, you may introduce her correctly.
Yeah, no.
Thank you.
Good evening and welcome to this public lecture. And today's speaker is none other than Dr. Shylaja, and she's familiar to everyone. And she's one of the noted science, particularly astronomy, communicator and educator. And she's there in the field for quite a long time. Professionally, she's an astronomer. She worked on ultra stars, and her PhD was here in IAA. And Professor Bhattacharya and Bapu, and yeah, so she worked with stalwarts of IAA founder directors. And she is closely associated with Jawaharlal Nehru Planetarium, and there, I think she's there for more than 18 years, 20 years, yes, and then out of which 5 years she was the director of the planetarium. And then she introduced quite a number of things there for public outreach programs, like universe in the classrooms. And she introduced some of those things, and also knowing what stars, those stars. So, so and she had quite a number of publications. To her credit, 120 publications I saw with the scholar, refereed publications, and then 17 books, varied subjects, some in English, some in Kannada, and so transit to Venus, and then the mirrors of mathematics. And so yeah, she is doing a phenomenal work for quite a long time. I mean, reaching out to people across India and then across Karnataka. And her main interest for the past few years, maybe earlier, the history of astronomy, and then she extracts the astronomy development in the country using the temples, the monuments, and the stored inscriptions and things like that. And there's quite a varied interest. And then today we're going to talk about astronomy development in India after the last 1,000 years. So, welcome, Shylaja.
So thank you for that nice introduction. And this is my homecoming. So all of you are familiar with me. I'm happy to be here, and I thank Mamta and Dr. Muthu for inviting me to give this talk. And I'm surprised that she remembers me after 16 years when she was a kid. And we met in Udaipur, not here. That's it. Okay, so today I'm going to concentrate on the development of astronomy in India during the medieval period. That's because when we talk about history of astronomy, usually we start with Harappa. That's the trend now. And Harappan civilization is concentrated to the banks of the Sindhu River. So these are the settlements, and this is where people start the history of astronomy. And at the last slide, I'll go back to this and tell you how important it is for us to change this now. So when history of astronomy was written, say 100 years ago, various British scholars have written papers and books on this. And among the Indians, the one striking name is Bal Gangadhar Tilak. And they start from the Vedic period, that is 1500 BC. And then when you talk about Shulba Sutras, it's not audible. Okay, is it better now?
Yes.
So it takes you back only to 1500 BC, and these texts called Shulba Sutras were not dated very precisely. But now there are 3 volumes of them, so one goes beyond 1500 BC. How they actually do it, etc., is different. But when these works were done, the existence of Harappa or Mohenjo-daro were not known. So now you have to change your chronology of Indian history of Indian astronomy. So that's where it stands today. And the monumental work by Marshall and subsequently by Devi Prasad and Kosambi's father and son, they introduced the Harappan concept into the history of not only India but astronomy as well. So volumes and volumes have come out after that in the recent years, including the Harappan civilization. So basically, why was astronomy needed in the ages, say 3,000 years ago or 5,000 years ago? That was basically they were observing the sunrise and sunset positions and trying to understand the relation to the season. It's as simple as that. And then, of course, the moon rise and moonset timings, etc., phases were observed to form some kind of a calendar, which was needed for their day-to-day activities. So it just limits us to that in the beginning. And of course, for navigation, because they were also traveling. So the need, then we will extend to other areas, namely the seasons. Why did they want to know the seasons? It could be because they were planning to hunt, and the pattern of hunting and then not hunting at some times of the year, etc., will have to be decided by looking at what's happening in the sky. And then the phases of the moon for day-to-day activities, for fixing any cultural festival or anything like that, and to mark the time, say, of the birth of a king or the coronation of a king or any such thing. But the most important is the onset of agriculture, because of which astronomy has its deep roots in folk literature, which is practically unknown today, not recorded anywhere. So go to any corner of India, the folk people will have some tradition related to astronomy, and that is the one subject which needs more attention. So this is the basic plan they would have started perhaps 5,000 years ago. So you mark the winter solstice and the summer solstice point, and then you put a second marker there, and that becomes your clock. So that is the way the stone alignments, etc., are found here. And then you realize that for the moon, it doesn't work. So we have to offset it by 5 degrees on either side. And there is a pattern in the 5 degrees also. So all these they would have noted with their observations. And a lot of such things have been found in India. Kameshwar Rao, Wahia, Sri Kumar Menon, all these people have worked on these kinds of stone alignments all over India. But I am particularly referring to this one in South Africa near, the river is called Komati River because this has its roots from India. So it's a place on the river Komati. And it's between Mozambique, border of Mozambique and South Africa. And it's called the chariot of the dying sun. So this is how the stone patterns are. And then these are perfect alignments for marking the winter solstice and summer solstice, which are reversed there. And so this is how it looks. And so you see the winter solstice, sunrise, 22nd June. So this is, it still exists and people go there for hiking, and the words that are written there and they are from India. So that is how they trace the origin of these to India. So I am showing this because you have many such things in India. I have given so many examples on which Kameshwar Rao, Wahia and Sri Kumar Menon have worked. But the other one I showed is in South Africa, so it should be interesting. So many of you who may go to Cape Town for a next meeting may plan a visit to this place and see this place. Okay. Then eclipses and comets we can understand. There must have been really some treat for the eye, and therefore they would have recorded it. So this is a painting of the total solar eclipse from Kavda. Can you see the eclipse? It's there in this corner. Yeah, I have highlighted it. Yeah, this part is here, so you can see the almost total solar eclipse. This is a painting from the Washington Museum, but once they put it onto the net, I studied this and I came up with some date, and Kapoor, is he here? He also studied the same painting, and we differed by about 50 years. Both of us arrived at the similar region because the author, the name of the artist is known. It's based on that. So such records you will see plenty in Europe, but in India it's difficult to find, and Kapoor has found one more in Amritsar. But then why did they need the stars and the planets? Okay, you need the sun for the year, you need the moon for the months, and eclipses are some beautiful sights in the sky, so you record it. Comets are beautiful things, and why did you need the stars and the planets? So this is the question that comes to mind. But of course, we have all those things. So the seasons, variation with latitude and longitude, correction for refraction, parallax, all these things were very well established by the medieval period. So we have people like names like Aryabhata, Lalla, and Bhaskaracharya, who wrote all those treatises, based on which the other next generation followed the work. And so all these things were very well established by medieval period before the advent of Islamic rule and of course the colonial rule. Now, the star name, this is what I'm trying to say. So in Mahabharata, Kritika, the name of the star appears as a star rising in the east during the time of Mahabharata. This word has been used for dating Mahabharata. So the name of the stars, 27 stars, were very well known for time markers during the months. So this is one place where we need to know the stars. So the 27 stars would suffice. And of course, you need to know about the pole star. And there are many more stars which were of interest. And so all these stars were listed. and they were observing these stars. For example, they would look at the star which is on the meridian and decide the time of the night. And this is memorized in the form of a verse. So they recite that verse and know if this star is there, then the time of the night is this much. This was the way the stars were used for measuring the time in the night. And of course, this is something, the effect of shift of the equinoxes, that was also very well known. So this is another point which you can use for dating historical events where no astronomer would have specifically written that I saw this happening, No such record exists. Even in the books by Aryabhatta or Rahamihira, there is no observation logbook. So they were never writing any such thing. So that is one thing that we are missing, but we have to indirectly infer that they would have done this or putting this calculation. I'll show one or two examples which will prove that they were indeed observing and then marking the corrections which were needed from year to year. So the 27 stars, as I mentioned, were markers for birthdays. See, for example, Swati Tirunal has been named so because of the birth star. The moon was near the star Swati, Arcturus, and so on. So this is a tradition which is being followed even today. So we have these 27 names very popular amongst us. And the references to the stars come for coronation and similar events. Not only in the Hindu or Jaina text, but even in Buddhist texts. Text we may not have, but we have stone inscriptions where these words are written down. So we will know that the stars were being used extensively. Star names. So, okay, this I said. And folk tradition, as I mentioned already, is one of the richest sources. And at least in Karnataka, we have a method of identifying the time of the year by these names. So which month is this? So they call it Malay Nakshatra. That is, the rites are named after this, which indirectly means where the sun is. So this is how the folk tradition has retained all these things from maybe 1,000 years or even much before that. So this is the example I am trying to show for understanding the meaning of what is Kritika at the time of Mahabharata. So we know that because of the precision of equinoxes, the pole is shifting, and therefore the pole star that we have now was not the pole star, say 2,400 years ago, which was the reason. And so you have Kritika being marked there, which corresponds to 2,400 BC. So that is how you are able to time the events that are mentioned in Mahabharata. Okay, so accordingly, the solstices and equinoxes are also cited in many stone inscriptions and in many texts, other texts. But when we come to, now this is all from non-astronomers. So what were the astronomers doing? So we get a clue of this from a text called Manasara, which is dated 11th century. All of you know that the declination of the sun keeps changing throughout the year. So if I measure the shadow of the sun at any time of the day, I will be able to fix the declination only at noon. But in the morning to evening, the declination would have changed slightly. It may be half degree, it may be 1 degree by that amount. And how did they measure it? And how did they apply the correction for that? That is given in Manasara. And this word used for this is called apachaya. So they were not able to decode the meaning of the word apachaya. Chaya is the shadow. So there is something that is to be appended for the chaya. That's the meaning. And this was decoded by Vahashi. And this is the formula that is, or the words that is given in Manasara. And when you convert it into a graph, it comes like this with steps. You see, like this. And then he tried to understand what is the meaning of this, because this is solar longitude, which is the time of the year. So you have to apply some correction, which is of the order of 1 or 2 minutes. depending on the time of the year between sunrise and sunset. So this small correction, which is only relevant for astronomical calculation, was incorporated into the text and was not known for the last till the last 50 years or so, till Uhashi published this. Because the word Abhachaya means this. This has not been written down anywhere. So that is how we get to know about this. So what I'm trying to say is that measurements of this nature, going to the accuracies of half a degree in the position of the sun, was being done, but have not been recorded in any log books, and we have to indirectly get to know about this. And we have all these books which were available: Surya Siddhanta, Vedanga Jyotisha, Aryabhatiyam, Pancha Siddhantika, Khandakatyaka. These are all prior to 10th century, except Siddhanta Shiromani and Siddhanta Shekara, they were 11th century. So all these books were available, but then what was needed for the later astronomers? The theory is already established. Now you have to apply correction so that all those calculations are valid. So the commentaries were written and the corrections were incorporated in the commentaries. So during the medieval period, a lot of effort went into the preparation of these kinds of corrections that are needed for the formulae provided in these classical texts, you can say. So that is where medieval period contribution begins. Okay, I will briefly mention the procedure that is adopted. You just count how many days have elapsed from a particular point, which is called the onset of Kali Yuga or something like that, which they tie up with Mahabharata and so on. Let us leave that aside. It's a particular day on which the sun and the moon and perhaps an eclipse also took place. That means from that date to today, you count the number of days. That is called as Ahardana. So how do you do that? So because you are using the lunar calendar and today's date will be mentioned in lunar calendar. Imagine there is no calendar available. So today you look at the moon and this is the 5th day of the moon or 7th day of the moon phase, etc. That's what you know. And how many full moons have elapsed from the beginning of this year, you know. So based on all these things, you will count Ahardana, which is a 9-digit number. It's goes to 9-digit number. Now, the Siddhantic text say that if this many number of days have elapsed, the planet, which may be the sun, which may be the moon or any other planet, would have covered so many revolutions. So that's the starting point. Yes.
Which planets did they know?
I am talking about the 5 naked eye planets only.
So 5 means moon, sun, and
Moon and sun also. No, I mentioned here the word graha means something which is moving in the sky. So the sun and the moon also were called graha because they were moving in the sky. So altogether 7. 7. Okay, 5 naked eye planets. They were called Taragraha because Tara means a star. They look like dots in the sky. So they were called Taragraha. So 5 star planets and 2 sun and moon. Okay, I'll come to the other one just now. Okay, so how do you increase the accuracy of your measurement? So you have measured something as per the formula. The moon should have been here, but it is here. So you have to add that correction. Instead of adding few minutes, they will correct the number of revolutions itself. That is how they were applying the correction. And the interesting thing is that we know that all these are elliptical orbits. The apogee of that, no, this is a geocentric thing. So they called it apogee and Mandocha they call it. That itself is changing the position. So how it is changing the position? So that was also a variable parameter that was used. And so for the sun and the moon, the correction is only for the elliptical orbit. For the other 5, their position relative to the sun, that also is another correction that is added. So that they have different names. One is called Manda, the other is called Shigra. So if you translate it literally, Manda means slow, Shigra means something is fast. No, that's not the meaning. The meaning is something different. And the interesting thing is that you have two epicycles corresponding to each of them, but you cannot apply them together. You have to apply one, go to that position, and from that position, you have to calculate the correction for the next one. So this was the procedure that was being followed. And this is one example where the corrections I'm showing. See here, this is 6th century. This is Siddhanta Shiromani, etc. This is about 11th century. Look at these numbers. The number of revolutions of the moon, it is running to 336, but here it is 300. So these kinds of corrections, they incorporated so that finally when you divide one by the other, the accuracy that you wanted is achieved. So this is how they were doing it. Okay. And then the mathematical formula also, a year is having 365 and a fraction. You all know that. And then when you want to calculate the number of days, you have to take care of the number of intercalary months. That's in the lunar system. We all know that we have an extra month sometimes once in 3 years to match the movement of the sun and the moon. So that you have to incorporate, and finally you have to get the total number of solar months. And we'll go to the next one because I try to rewrite the formula in a better way. Okay, here it is. So they knew that the duration of the year was 365 days, 15 Galige. So 1 day is consisting of 60 Galige Argatica. And then this is 1/60th of that called Vigalige. This is 1/60th of that called Pare. This is 1/60th of that called Tatpare. So this, they knew it to this accuracy. Now I am able to write it like this, but they did not write it like this, but they prefer to write it in these kinds of fractions. So if you want to calculate the intercalary ones, this is the fraction. So every time you want to do this, you will have to be working with such big numbers. Instead of that, they modified it like this. So in this, the book will say, take the number of days and then add 5, divide by 976. And then this itself, you divide by 14945 and take it out. This will be the verse. What is the meaning of this? The meaning of this is, this will take you to this number to a certain accuracy, and you will need to have a correction only after 14,945 days. That's the meaning. So they have to keep track of this, and then once it crosses 14,945 days, then you will apply the corrections. Then in terms of the months also, it is the same thing. So this is written in one book, this is written in one book. And then this number 916 changes to 903 in later text. So this is how the corrections were being incorporated from time to time, which we will get to know only from the text of the medieval period. So this is how it was done. And then in about the 14th century, the sign tables were ready. 11th century itself, the sign tables were ready because you have to calculate the correction as a sine function. So the sine starting from 1 degree to 90 degree, 1, 2, 3, 4, all the things were available. They were memorized. They were available in the form of a table. And you could have interpolated them between 10 degrees. So this was also possible. But in about 13th century, they learned how to express this as a series. We all learned that in our mathematics, how to express the sine formula as a series. This was known to reduce the time needed for the calculation, but to a great extent. And then we also see that the elements of calculus were already introduced by the time of Bhattacharya. So, sorry, Bhaskaracharya. For example, if you want to calculate the instantaneous velocity, and if it is moving as a sine function because the projection you are taking, the differential of a sine function is cos. So he says directly you take the cos of this angle. So till then the velocity etc. was being mentioned as sine, but suddenly it changes over to cos, which means something you know already. So this is the kind of hidden meanings that are covered in these Karana texts. So they knew Tatkalika means you have to take the differential. So a sine function becomes a cos function. So this is what. And then these people the challenge was to calculate or predict the time of the eclipses very precisely, especially total eclipses. So this part was done by a few astronomers, and the tedious calculations fetched them some timings which were verified. And at the end of that, they were honored. How do we know that? There are stone inscriptions wherein they would have written that so and so was honored, such a big astronomer was honored. Usually this will be following one or two total eclipses, so we know that it must be because he calculated that very precisely also. And from these stone inscriptions, we also get to know the names of some astronomers whose work we are yet to find out. So that way, we were lucky to get one or two names for those things are available as palm leaf manuscripts now. Okay. So in the medieval period, it was all commentaries, and we have so many commentaries, 17th, 11th century onwards. So you can see right up to here. And here, see, he says number of solar months, he simply says add 10. Where is this 10 coming from? That is his own correction. The author has said that I have added 10 so that I get this correctly. So that's the correction. From then onwards, people will have to follow. And I told you about a number 903. It becomes 900. So it has to be subtracted. And so on these kinds of corrections, we find only in this text as commentaries, which were written in the medieval period. Okay. Okay.
So was there no interaction between these various astronomers?
Yeah, there was.
Interaction between
Yeah, because you can see the cross in the opening of every book, they will say we are indebted to these astronomers who have taught us this, and there you will find all these names. So some names, for example, there is a place called Bhid in Maharashtra. There was a school of astronomers there. We don't know anything about it today. But some of these texts will say that a great astronomer from this place has taught me this. I am grateful to him. Things like
No interaction among contemporaries.
yes, it was there. For example, Siddhanta
So that the
Shiromani,
corrections can be uniform across the places, right?
I think they were exchanging.
Okay.
So when he said that I'm adding 10, he doesn't tell that I am doing it myself.
So
You see a contemporary text, there also I will say, yes. So there was a good interaction.
Did they mention why they thought these corrections were needed from time to time?
No, why part is not there.
They
This is
don't
they,
get
because
into
this,
as to why they needed it.
no. They knew that it's not such a uniform motion that they are seeing in the sky, so they needed the corrections. That's it. Now, instead of telling you all those corrections individually, I am thinking of presenting to you a different way. Namely, I will compare the different methods over, say, 400 years. So, I have taken a book by name Grahanamala, and I'm going to do this for one particular solar eclipse. Grahanamala, interestingly, is a book written by a king who was a small-time king called in some part of North India. I don't know the name. He was conquered by the Mughal Emperor Akbar when he was arrested. He sat in the prison and he prepared this table of a canon of eclipses from 1600 to 2600. So he prepared this table and Akbar was impressed, and so he released him subsequently, and then the book is available in print form now. And then I have taken the other one. This is a book in the Oriental Research Institute in Mysore. It is a canon of eclipses from 1800 to 1900. And then this is the book written in 1604. It has changed the pattern of calculation by introducing the 7-day week concept. It's used for parity check. And then you have another 100-year-old book which is available in printed form. It is a method adopted from V.B. Ketkar, who was a very well-known astronomer. He uses the 19-year cycle for fixing the epoch very precisely, positions very precisely. I have taken this eclipse, August 18, 1868. All of you know the importance of this. And the path passed through South India. So many people have done the calculations for this. The team of Italians and British, they all have made the observations of this. So how would this be according to the four texts? How the timings match? This is what I have tried to show you here. And you know about this helium discovery, etc. That's what we know today. So this is the eclipse I have chosen. So the first book is this Grahanamala, which is available in printed form. As I said, this is written in the 1600 around that time. And all of them generally do the calculation for Ujjain. Ujjain was the time. So the total duration is 2 hours, 20 minutes and 48 seconds according to that. But from any ephemeris that is available online, not only NASA, XJupiter or any such stellarium, you'll get it as 2 hours, 31 minutes and 21 seconds. And then the next one is Grana Darpana, which is in Mysore. What method they have used is not known. And this eclipse is covered because it is in 1868. And this is the way it is written. The text is written like this. And then they give the figure here and indicate in this where it is the first, second contact is and where the third contact is. That direction will be mentioned. So this is how the book is. And this gives 2 hours, 51, 56 seconds and compares with 2 hours, 51, 32 seconds. And then the third one is this book dated 1604. He has given only the method. I did the calculation as suggested in that because it's a method which is different from the other earlier ones. So here you see a difference of 1 minute, 2 hours, 52 minutes and 40 seconds and 51, 20 seconds.
How did they time it?
Huh?
How did they time it to the seconds?
This is calculation. This is calculation.
Calculations from formulate.
No, I told you they don't keep a logbook. They did not say that this matched or anything. No, how do you know indirectly that it matched? Somebody would have given them an award. Okay, there also there is a problem. Even in Chinese records where the logbook was maintained, you won't know whether it's a total eclipse or a 99% eclipse. Because from the naked eye observations, you cannot make up. Right? So this kind of ambiguity is there. But what I'm showing you now is only the calculation part. There is no record of any observation. Then the last one is the 1910 text, which is based on V.B. Ketkar had understood all these problems and he incorporated the corrections as was applicable for the year 1860 or something like that. So he must have observed this eclipse, but I don't see that mentioned anywhere in his book. But he has mentioned about having observed the 1874 transit of Venus. But this particular eclipse he has not mentioned. So here also the difference is only 20 seconds. This means from time to time, the corrections were being incorporated. So this is the approach we have for the medieval period. And the interesting point is the, yes.
Eclipses were also which location?
Ujjain.
All of them.
But Ujjain did not have total. So I had to apply the correction for, see, one place was Sringeri, the other was Mysore, and the third one just says 18-degree latitude, and the name of the place I do not know. Maybe it was somewhere in Maharashtra. Somewhere there is a name of the place starting with a M. I don't know whether that town exists today or not. Male or Male, some such name is there. The interesting point is this, she asked me about the 7 planets. These are the 2 other planets. Okay, these are all the also points which are moving in the sky. What are they? These are the nodes of the moon's orbit, ascending node and the descending node. I consider this as an ingenious concept because they knew that the 2 points were moving in the sky So they gave it the status of the planet. And so they were able to calculate the position of the node very precisely. How did they do it? That's the part. So they were watching the movement of the moon meticulously every night. And when it crosses the ecliptic, that point they had to write down. So they must have been doing the thing very precisely. So Rahu and effectively 8 planets, Ketu is one diametrically opposite to it. So that is how these Rahu and Ketu names figure in, but no astronomer uses this. No astronomy text uses these names, Rahu and Ketu. They call it Pata Bindu or Parva Bindu or something like that. But only the other texts, non-astronomical texts, they like this word, they like the story associated with this, so they use these names. Okay. I was studying the 12th century, 13th century table. It's just a table of numbers for the 5 planets. And so I was able to get this graph done, which shows how it matches. This is the longitude of Jupiter and Saturn. All of you saw this conjunction beautifully happening. So this is the way it matches. This is the precision correction that is needed. And also the beginning of the year, so it gets offset both in this direction and this direction, because all the calculations that I talked about hitherto did not take into account the precision correction. But they definitely knew about the precision correction, because without that, you cannot get the declination. So the declination is defined by the point where the ecliptic and the equator cross. And therefore, they knew about the precision correction. Whenever they wanted to know the declination, they would apply the Ayanamsha. That was the word that was used. So for these texts, it used to be something like 16 degrees or 18 degrees. Today it is 24 degrees. So they applied this correction, got the declination value. This was known. And Graha is a bird which is something that is moving in the sky. So they called this Ayanamsha also as a Graha. They assigned a period of 25,000 years for this. And then, just as you would calculate the position or the correction for something which is known to have a specific orbital period, they would calculate the precision correction for this, which works out very well. So the word Graha here is not to be mistaken to mean a planet like, a body like Venus. And this 13th century table, I have compared here. So I have compared it with the XJulia. This is a free site where from there you can get the ephemerates for any year. So now you see how it exactly matches here. So that means if you apply the precision correction, this will go up here and matches with that. And you also have to move it this way because the beginning of the year is slightly offset. Okay, because it's lunar calendar that is used. Then these texts that I am referring to as tables were called Karanas or Sarini. Sarini is a table of numbers, whereas Karana is the same thing stated in the form of a poem. So you recite a poem, and for every year you compose a new poem. So that's the kind of method they use for memorizing the things, and that's where these poems were circulated. And everybody would know what is the poem for this year. Last year's would be forgotten. So this year you will have a new poem and you memorize that and calculate all the positions for that. So the type of corrections I have already mentioned. So they were excellent mathematicians. So they were able to apply these corrections. And that's when I feel that the regional languages will have more input in this direction. So Kannada, Telugu and Malayalam and even Tamil. Tamil is a problem because nobody is able to read that and understand. But unfortunately, in the other languages, people have come up with these things. So I took this Sarini from the 13th century origin, and then I have matched with the exterior and see how finely it fits. This should have continued like this, okay? But I deliberately wanted to show it changing from 360 to 0. Even that happens on the same day. So to that extent, it matches very well. This is for Mars. This is for planet, position of planet Mars for a specific year. And the table simply gives the numbers. So you will have to understand how to decode that and convert that into a graph. So this I mean, this will be known to only some selected people. Not every common man will be able to appreciate the use of a table of this nature. So you know about these things. I don't have to spend time on this because these are very well known. This is because I'm covering the medieval period, the various efforts to improve the accuracies of observations was attempted by Jai Singh. And generally, even when Dr. Ratnashri was trying to use this for current observations, she was only concentrating on daytime observations, shadows, and the shadows will become very diffuse and so on. But these are more relevant for night sky observations because you have a sighting tube and your positioning can be as accurate as the point, the arc second there. So that part has not been verified so far for these instruments. And then comes the Islamic rule. The effect we will start seeing by about 13th century. Before that, it was one way. The Arabs came here and took the books from here. But the effect of that, the return thing, we come to know only by the introduction of this instrument called the astrolabe. This is basically an Arab instrument. And these are the various parts of the instrument. The most important is this. This is the plate which defines your latitude, which is the job of the astronomer to create this. And then this is the red dial, which is it's a star dial. Every point here corresponds to a star, and the name of the star is written here. So you can move it. It's a movable thing. So you measure the altitude. For measuring the altitude on the reverse side of this, there is a sighting device, this one, with two holes. So we measure the altitude and then come back to this dial. From the altitude measurement, get the other right ascension, declination, whatever you want from this dial. So this was a very handy dial. And very quickly, this instrument was adopted by the local scholars. And then there were families in Lahore and Gujarat known for producing excellent quality of astrolabes. The other thing that happened during the Islamic rule is the translations of these treatises from Sanskrit to Persian, and then they were carried to Europe via these countries. So this is the very brief summary of Islamic rule. But then you see this in Jaipur, the instrument was widely used here, and you can see the size of the astrolabe, so what accuracy they would have achieved by using this kind of a device for the position of planets and even stars. And I show this particular one, which was from Ahmedabad. This is with some person in Brussels, a private property. And you see the numerals are in Devanagari. So the Islamic instrument was adapted to local usage. And this is the closer view of this. And this particular thing is very important because this was designed in 1605. And these are the names Shravana, Vega, Swati, and all these stars. And supernova, there is an extra tip here corresponding to the 1604 supernova. That's how this particular astrolabe becomes very, very useful. So here I have given the all those points here, and this is the location of the supernova here, that is here. So when this instrument was studied, say last 50 years ago or something, They were trying to identify all the stars, and here they were not able to identify anything corresponding to this. And there's a faint star here, New Sagittarius. So the catalog says it is New Sagittarius. But then I look back because New Sagittarius is something that doesn't match with the magnitude. Then this number gave me the clue 1605. So this must be the supernova, and it matched perfectly. Then these French astronomers who came, I'm covering the chronological thing, so we can't forget this person, Le Gentil. I don't know whether I'm pronouncing it correctly or not. I mean, that's how it is. And he is called an unlucky astronomer because he came to observe the transit of Venus and missed both of them for some reason or the other. And he spent these 8 years very usefully here. So I consider him a lucky astronomer because he was able to, he observed from Pondicherry. He was in Pondicherry. He produced 2 volumes. These are the 2 volumes. This has all the information, not only of astronomy, but the flora, fauna, lifestyle, social, cultural aspects, traditions, everything is into whatever he saw, he has recorded it there. And he learned how the traditional scholars here calculate the eclipses. So he learned that method and wrote that for the benefit of the people there. So that's a very useful thing. So I think he was a very lucky astronomer because he was able to do all these things. He was unlucky because he lost his property there. They declared him dead, and all his property was distributed to various people. But maybe he got it somehow later on. I think it was all distributed. He was penniless when he landed there after
His name is Le Gentil, means the kind.
Oh, I see. Okay. And he carried many flowers from here. So he named some of them after some great mathematicians. His life is very interesting because he had so many shipwrecks and he had to suffer from many terrible diseases, but he managed to he finally reached France by foot. Okay, so you can imagine how he must have struggled. Okay, then as far as the traditional things is concerned, this one name, you have his book here in the library, Kala Sankalika. John Warren, he worked in the Madras Observatory. He was another person who studied the method of calculation of eclipses by Indian scholars. And he wrote them for the first time in English, and it was discussed in Royal Society also. So this is one important thing because that's when slowly this got written in English and French. So people there in Europe also came to know about the depth of knowledge that was already existing in India. So the impact of collegial regime on traditional scholars, the families suffered, I should say, because this was after 19th century. The system of education changed. So there was only a small group of astronomers who were left isolated from the mainstream. And they were the only ones who retained all these knowledge for themselves because the others didn't bother about it. Unfortunately, that's the one we are able to lay our hands on today. So they have preserved the palm leaf manuscripts in their houses very religiously. They kept it very safe. And so we are able to read them today. And some came forward to translate them into English and French, joined hands with the British people. And so the 2 names that I mentioned, Bapu Deva Shastri and Sudhakar Dwivedi, they did a lot of work in this aspect. And that's how all of us are able to read it today. Otherwise, we would not have known it at all. And this is a typical classroom photo which is available on the net by Bapu Deva Shastri. So this is the globe. He is using the globe to teach a group of students about astronomy. So this is a classroom in Varanasi. And then you know about the establishment of observatories. This institute itself has a long history. So I don't have to tell all that history again. So Madras Observatory. And of course, Thiruvananthapuram also had an observatory by Swati Tirunal. Lucknow, Dehradun, and many more were there, but eventually they were lost. Fortunately, Madras and Trivandrum are still surviving. So they were exposed to the new techniques of measurement. See, even when the telescope was brought and given to Jai Singh, it was only a tool to see the things. But then the actual process of measuring the position of the star with a micrometer kind of a device was not established. So he was not able to do any such measurement as such with the telescope, although he used and monitored and measured the position of the satellites of Jupiter. But these things developed even in Europe subsequently, and gradually they were transferred here, so people here came to know about it. And there were many attempts to blend the traditional methods with these European techniques. There, Chintamani Raghunatachari from Madras Observatory has a great role to play, but he did not succeed. Same with Kepler. He predicted the position of Pluto in 1911 itself. He was well versed with the Besselian method of calculation. So this is the year. So he had predicted the position of Pluto here based on the alignment of Neptune and Uranus. He calculated it just as you do it for Galilean satellites. He extended the same method for this, and he had done this in 11 itself. But you know that Tombaugh discovered it almost 19 years later. So it was known, but it was not publicized at all. Similarly, the comet discovery by Subramanya Iyer from the Trivandrum Observatory is not known to people at all. He lost his chance because his report reached late. By then somebody else had already submitted to the Royal Society, and so the comet got that Russian fellow's name. And we have to remember this Pathani Chandrashekar Samanta, because he did not believe the European methods at all, and he continued in the traditional way, and these were the instruments he designed for himself for making observations. And even in his book, he says that the other people say that Earth is not at the center, but I don't believe them. I believe that the Earth is in the center. But all the rest of the, how does it matter for calculation? Because you are making only relative positions are needed. So his calculations were perfect. He observed the transit of Venus and so on. So he was the last scholar, I should say, who depended only on these traditional methods. And then the efforts to revive the tradition, Raghunathachari and Bal Gangadhar Tilak also tried to do this. And there was one Kalinath Mukherjee in Calcutta who also tried to introduce the Western astronomy to common man. They were not very popular, but for copying the names. And of course, the monumental work is by Shankar Balakrishna Dikshit. There are 2 volumes of them. Single-handedly, he prepared these 2 volumes. He traveled all over India, spoke to the traditional scholars, and found out what were the books available, what were the manuscripts available. He made a list of all those things, and that's a source book even today, although he wrote it 120 years ago. And on a small scale, some instruments and some teaching is going on in several small places and not highlighted anywhere. That way, this online catalog, descriptive catalog in Indian astronomical instruments by S.R. Sharma is very useful. It's a 3,000 page volume available freely on the, anybody can download it. In fact, I downloaded the image of the astrolabe from this only. And he has included even this thing in Mysore. This is still existing. It had been in very bad shape till about a year ago or so when I went and asked for it. I said, I'll take it to the planetarium and display, please give it us. This was prepared in 1930 or so by a scholar. What is his name? Sheshachar. Karuru Sheshacha. That's the name of the Mahavidwan. So he prepared this as has been described in Bhaskaracharya Siddhanta Shiromani. This was being used, but after his time, this was junked. So that's when I went and asked that we want that instrument, we will display that in the planetarium. Then they got it painted, and this is how it is in Mysore now. They use it for teaching what is called as Jyotisha, which is mostly astrology, unfortunately. And this particular book by S.R. Sharma has this instrument listed, and all the astrolabes which are scattered all over the world, made in India. That's how I came to know that Lahore and Ahmedabad had a very strong group of instrument makers. So that's all listed there. It's a very useful source for this was online only 2-3 years ago. And so a lot of more work in this field awaits scholars. Only 450 out of about 9,000 texts have been edited so far. So post-independence, I have to remember these 3 pioneers. K.V. Sharma, there is an institute in Chennai. K. Shukla was here, I think. He gave a talk here. I don't remember, must be in 78 or 79. Those days, I did not understand any of the things that I confess. I did not understand anything I sat here and listened to him, but I did not understand anything. Ohashi, he passed away only 2 years ago. He came from Japan and worked with Shukla. And he was the one who brought out all the details of the instruments that are described in the various texts. And of course, R.C. Gupta, a very great mathematician, and Balachandra Rao here in Bangalore and his group, they have come out because all these medieval texts are receiving only attention now. And it's my duty to remember all these people who have brought this to light. So I started with Harappa, but someday we may have to revise the history of astronomy again, because I have found that you have traces of them in this part also. Here also you have a lot of information on the Indian calendar system, the so-called Hindu calendar. I don't like to use the word Hindu calendar, but that's how the books are written. So this is the Silk Route. The Silk Route may as well be the astronomy route also. So here you have in this part of Asia, and even in this part of Asia, you have a lot of influence of the Indian eclipse calculations and so on. That 1868 eclipse, which I mentioned, was observed from Thailand, and the king there was able to predict the time of the eclipse using Surya Siddhanta. That's what he has declared. So it was very well known. Therefore, we may have to change the history of astronomy, not only from Harappan time, but maybe with this we may get some more information. We may have to push it back also. So that's where I stop. So I think I have conveyed some information about the medieval, what happened in the medieval period in Indian astronomy. So thank you for your attention.
Thank you, Shylaja, walking us through progression of astronomy in India during medieval period. Will you take some comments?
Yeah, sure.
Are there any comments people want to make? Yes.
Thank you, Lance, for such an informative talk. I have a couple of questions. First one is there any written thing like the distance from Sun and Earth or Moon and Earth in the medieval history?
Yes.
How this calculation?
Yojana. They use the unit called Yojana. 1 Yojana is approximately 5 miles or 8 miles, depending on which text you are using. So they always talk in terms of the ratios, but even the circumference of the Earth, the distance to the Moon, distance to the Sun, everything is given in yojanas, but there is a very serious error in the case of the Sun. Okay, but the Moon is okay.
So is there any way to define how these calculations are done?
Is there any?
How these calculations are done? Is it written?
No, it is not written. That way, how did they calculate 5,000 yojanas is not written. But you can infer it. He describes that there is an observer standing on the equator. There is another observer standing at the pole. If not pole, 90 degrees away, then what is that angle? He defines parallax. So you know that that's the method that must have been used for calculation. So directly he does not say I stood here and observed and so I got this number. No, that is not written anywhere.
Yes, next question is, as you said that they calibrate the planetary motions. So is there any idea about retrograde and
Yes,
prograde
of course. That's the second correction I talked about. See, I told you about two corrections. The first correction is for all planets. That's called that's for the elliptical orbit. The second correction is relevant only for these 5 planets, which is relative to the position of the sun. So at what position of the sun, it starts going backward. This angle will be specified. And so they say Bhauma. The Bhauma means Mars, the son of Earth. That's the meaning. So that's the mythological name. So Bhaumari means they always give it in the same sequence. First Mars, then Mercury, then Jupiter, then Venus, then Saturn. In the same sequence, they simply list out the numbers. Those numbers are at what angle the retrograde starts, at what angle it stops. So this is very clearly defined in all the texts. They knew about it very well.
Thank you.
Yeah, you have mentioned in one of the slides that 1 day is divided into 60 Gatikas or something. So why 60 has been taken?
No, I don't know the why part. I see that they have done it. Okay. So you can speculate anything for that. But 60 is for convenience because the next unit is again divided by 60. The one is also divided by 60. When you go to the angle, again divide by 60. See, they were working with fractions. So multiplying a fraction with another fraction, if they're all on the same side, whether you are using the angle units or whether you are using the time units, the multiplication becomes very easy. So 60 is the...
Brilliant.
Thanks. What about catalogs? Did they make any stellar catalogs or something?
Stellar catalogs are all with yes, I have studied 2 catalogs. One is dated 15th century. It lists 100 stars. Again, it's not a table, it's verses. So all the numbers, the longitude and the latitude are written in terms of words. That's called Bhuta Sankhya. Bhuta Sankhya means you express a number as a quantity. If you want to say 2, you say ice. That's the word that is used. If you want to say 4, you say Vedas. No, it's not Katapayadi. This is called Bhuta Sankhya. Katapayadi also is used. So Ramaloka is a Katapayadi thing. Ramaloka means Ka means 1, La means 3, and Ma means 0, and so on. So that is how you have to read backwards and get the number. Whereas Bhuta Sankhya is objects. Bhuta is an object. So all these numbers are written down. So to decode those 28 verses and prepare a table, it took me 3 years. The table is done. Okay. So 106 stars. 106 stars.
Coordinates?
Yes, with coordinates and magnitude.
And magnitude.
Pramana, they call it as Pramana. So Dvimana, Ekamana, first magnitude. Sirius is first magnitude, and so on. It's there.
And the coordinates were what?
Coordinates for that particular thing, and then they give what is called as Paramonatamsha. That means the maximum altitude. Maximum altitude is given. So from that also you can calculate the declination, provided you know the latitude of the place. I used it to get the latitude of the place. It's somewhere near Delhi. It's not Delhi. Slightly to the north of Delhi that he has prepared the fact. So I was able to use it. His name is Nityananda. Nityananda, unfortunately, is known today. Famous for the different reason. His name is Nityananda. This is about 14th century.
Are there anyone online? No
I just
questions?
have a quick
Oh,
question.
please.
Yeah.
So during our observatory open days, sometimes, people they come and they ask how close or how far is astrology with astronomy? So how do you explain that to general public?
I bifurcate them. First of all, I will say I know nothing about astrology. What I'm going to tell you is only astronomy. Okay. So when they say astrology, they mean predictive astrology, right?
Yes.
So that is something which is not written by any of these fellows. Okay. So none of the astronomy texts that I've mentioned so far talk anything about astrology or prediction or anything. So when they write a horoscope, it's a measure of time. If you want to mention the time, a particular calendar is followed in this part of India. You go some 100 miles away, then there is another calendar according to that king. But then the sky will not change. Therefore, they mark the positions of the planets, the sun and the moon, and then the 60-year cycle. So if you make a mistake, you will be off by 60 years. So if they say Prabhava is the name of the year, Prabhava can be this or the one which is 60 years or 60 years that way. So that way this year's horoscope was only a measure of time. So that for writing that, you need the information about the planets. Okay.
I just missed the concept you said for Rahu and Ketu. What could be the thing? You had an explanation for that. I just repeated. I missed.
No, Rahu and Ketu are the two nodes. Rahu and Ketu are the intersection of the moon's orbit and the sun's orbit.
Okay.
So ascending node and the descending node. So these 2 points,
These are points which are reference for them.
they have a period of 18.6 years. That is known.
That's right.
And this is in retrograde. If the planets are moving in this direction, Rahu and Ketu are moving in this direction. So for all corrections, they say this all corrections are additive except for Rahu, they will say, because for Rahu, the correction will be in the opposite direction. So they consider Rahu as a planet, fixed its position by calculations using the same method they use for the 5 planets. The only difference is that it has a period of 18.6 years and it is moving in the opposite direction. So this they knew.
Interesting that they could use as an abstract concept.
No, how will you make a common man understand it? So you create a story and call it a demon. There is a demon sitting in the sky and that's the position and so on. The astronomers know what it is. But a common man will not understand. So you have to create a demon so that they will remember.
Thank you very much.
Okay, thank you. Thank you for
Beautiful research.